Today I want to talk to you about the geometric distribution. And let's start with considering this experiment. You toss a fair die until it lands on 4. A key word here is until, so just keep that in mind. Our goal is to calculate the probability it takes 3 tosses of the die to land on 4. Okay. So let's begin with our solution. One thing that I'd like to note is that our random variable here is the number of tosses of the die until it lands on 4. So I'd like to point out this random variable is discrete. So let's just note that. X is discrete because the number of outcomes associated with this, well, X could be, we need at least one toss of the die to land on 4, so X has to start at 1, okay? Another possibility is that it takes 2 tosses of the die, that's 2. Another possibility is it takes 3, 4. This keeps going infinitely many times. So even though X is discrete, it could be infinite, but it's what's called countable, or a correspondence with the counting numbers, 1, 2, 3, 4, etc. So X is still discrete. It corresponds with the counting numbers. Okay. Let's complete this table. And let's note one other thing. There's a probability of success. That success is the probability the die lands on 4. This probability of success, that's just given by the theoretical probability by theoretical probability. We have 6 outcomes. It's a die, right? So it's labeled 1 through 6. There are 6 outcomes, so the denominator here is 6. And only one of those outcomes is a success. That is landing on 4. So probability of success is 1/6. So we're going to have the event, we're going to have P of X, etc. Okay, and we're going to complete this table. So one event is that X is 1, there's one toss of the coin. The die lands on 4, so we're going to have success. The probability of success, P of X equals 1, is just going to be 1/6. The next row in our table is that X equals 2. It takes 2 tosses. So the first event must have been a failure. So we also need to know, hey, what's probability of failure? Probability of failure is probability of not success. So 1 minus 1/6, which is 5/6. So the first event is failure. The second event is success. You might ask yourself, could we have success then failure? No, if we had success then failure, we wouldn't have the second toss of the die because our criteria is to land on 4, then we stop. So P of X equals 2, that's equal to probability the first is a failure and the second is a success. This and probability, that tells us we can just multiply the 2 outcomes together. Okay, and we can multiply them because the outcomes or the probabilities of the die are independent. One fair die does not affect the toss of the next fair die. Okay, so probability of first is failure times the probability of the second is success, and that's going to be 5/6 times 1/6. Okay, so that's probability x is 2 in this chart. Now let's do x is 3. That would be 3 tosses of the coin. So we must have had failure on the first, failure on the second, and success on the last outcome. Success always has to come on the last value of x, because if it occurred earlier, we wouldn't have continued tossing the die. So probability x is 3. I'm not going to write first, second, third, but it's probability of failure, failure, success. And I'll put these ands here. Just like last time, we can multiply them, and we get 5/6 squared times by 1/6. This is the solution that we've been looking for. But we're going to take this one step further. So we've answered the question. If we wanted x is 4, it'd be failure, 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 success. So notice probability x equals 4. We'll use similar arguments. I think based on the formula above, we can kind of guess or infer, hey, there are 3 failures, so this will be 5/6 cubed. And then the last outcome is success, 1/6. If we had to guess a general formula, like k, probability x equals k tosses the coin, well, this will be probability x equals k tosses, or k trials. This will be 5/6. There must have been k minus 1 failures, then the success of 1/6. So this is a slightly generalized formula, but we can take it one step further. So in general, if our random variable x is the number of trials or tosses of a die in this instance, so k is the number of trials until, well, we needed one success. So until the first success. The probability of success is going to be given by p. Each trial is independent. Then we can use this nifty little formula. Okay, and this probability density, which is given by f of x, or probability x equals little x's, is how they write it in most textbooks. Then we can use this formula. Instead of having 5/6, we'll have the probability of failure. That's 1 minus p. After all, 5/6 and 1/6 are related by taking 1 minus their quantity. And we have k minus 1 of those multiplied by p. And one last thing is that there's only one of 2 outcomes on each trial. So let's add that. So this is the density function of a geometric distribution. Okay, in this instance. And you'll see in future examples we will use this density function if it meets these criteria, the random variable being the number of trials until the first success, having one of 2 outcomes, having independent trials, and a fixed probability P of success, then we will use this formula to solve problems. Thank you very much.